welcome back to Fat Mama Physics. This is the last video on uncertainty propagation. This video, we are going to look at exponents. So what happens if you take your number and let's say you are going to take it to an exponent such as 1 or 2 or 3, etc. Okay, so let's get down to business. Before we start, I just want to point out the numbers that I will use in this video are in the top of the page, so that we have A, B, C up at the top. And also, just to reiterate the fact that I expect you to know what a fractional uncertainty is, what an absolute uncertainty is, what a relative uncertainty is. I'll be using those terminologies in this video. So let's get started with exponents. For taking your number to an exponent n, what you want to do is you are going to multiply your number's fractional uncertainty by the exponent itself, okay? And then you're going to need to take its absolute value. So what does that look like? It's like these two bars. So essentially what that is let's say you have a negative exponent, okay? And you're going to get a negative answer. No, you don't get the negative answer. You take the absolute value. So let's say you have negative 2, for example, as your number. That's going to just give you a final answer of 2. So that's just saying, okay, we're going to shave off the negative sign because the negative sign has no significance, because when we talk about uncertainties, we say plus minus anyways, okay? In your data booklet, that's what it's going to look like. So let me show you quickly. If you are taking an exponent, if y, which is your final answer, is, let's say you take a to an exponent of n, then the fractional uncertainty of your final answer is going to be the absolute value of your exponent times the fractional uncertainty of your a, okay? There's actually significance to that. Do I have any quick question? No, I don't. Okay, so I'll make it up. Okay, I'll make one for you because it's interesting. On your data booklet, so I'm going to write this down here quickly. Notice again that you're going to get a fractional uncertainty this way. So you still need to multiply this fractional uncertainty by your final answer y to get its absolute uncertainty. Okay, so that's very similar to multiplying and dividing, if you must say. Okay, so here we have some examples. I think B is easy. This example 6 is easier to do, so maybe I will do 7 and 8 together with you, and then I will give you a chance to do example 6 by yourself. Example 6 shouldn't be too bad, okay? So starting with example 7 is we have square root of c, and that's going to be equal to our y. If you remember, or if you're not sure what the exponent is when you're taking a square root, it is not 1, not 2, but a half is going to be your exponent. So n is a half, okay? That's important to know. Well, of course, the first thing that you want to do is you actually want to take the square root of c, and if we take a look at our numbers at the top, c is 9 meters plus minus 1 meter. So I'm going to quickly write that down up here for our reference. And so we're going to take the square root of 9 meters. I wish that was meters squared. Okay, so that's going to give us, that's going to give us 3, because the square root of 9 is 3. And then for our units, that's going to be meters to the half. So we do the same function to our units as well. We leave that for now, because right now we're going to find the fractional uncertainty of your answer right now. And that's going to be equal to the absolute uncertainty of our n, and our n here is a half. The fractional uncertainty of c is 1 meter over 9 meters, and then our closing that absolute value sign, we have 1 over 9 divided by 2. Putting that into our calculator, that's going to give us 0.055 repeated, it looks like, okay? 0.05 repeated. And of course, this does not have units because, again, it's a fractional uncertainty. These 2 meters canceled out. And looks like it is also greater than 2% relative uncertainty, so I don't need to worry about rounding off to 2 significant figures for our absolute uncertainty. Now, to find the absolute uncertainty of our final answer, which is 3 meters rooted, this is going to be 0.05 repeated times our final answer y, which is 3 meters, or 3 meters square rooted. So that, if I do that, multiply by 3, I am going to get 0.16 repeated. Okay, and now that I can put in the units, which is meters square rooted, and to write my final answer, I'm going to round this to 1 significant figure, so the 6 is going to round the 1 up to a 2, 0.2 take the square root of meters, and then my answer, which is going to be 3, hey, is nice and perfect 3, but to show the consistency in the place values for my, between my uncertainty and my number, I need to put a 0 here. Again, this is meters rooted, okay? Don't forget to make sure your units are correct and the significant figures are correct as well. Okay, so that's example 7 with a square root sign. So I'm going to do 8 and then you do 6. I leave the easy one for you. Of course, if you want to pause the video and you want to try 8 right now, this is the time to do it. Now I'll actually walk you through it. I'll walk through 8 and then I'll do 6 on fast play for the solution. So here goes. 1 over a squared, I'm going to put that as y, okay? And if I go to the top of this page, I remember the value for a was 7.48 meters plus minus 0.03 meters, okay? And as for, if I have to assign an exponent for a, this is equivalent to a, and instead of 1 over a squared, this is equivalent to a minus 2, a to the power of negative 2, okay? So my exponent is going to be negative 2. All right, now I can actually solve for y, which is 1 over 7.48 meters and all of that squared. This is going to give me an ugly number, 0.01787. And the units that I will have will be meters minus 2. Okay, and then I can go ahead and find a fractional uncertainty of my final answer. And this time, in absolute value, I am going to have not a half, but negative 2, which is my exponent. And then delta a over a, which is my my fractional uncertainty, is going to be 0.03 meters over 7.48 meters. And then I'm going to get a number, which is 0.008021. Okay, and notice that after I took the absolute value, I don't have a negative sign remaining. No units for this one because it's a fractional uncertainty. So now if I want to find the absolute, ooh, ouch. Take a look at this relative fractional uncertainty here is going to be less than 2%. I'm going to need to round my absolute value to 2 significant figures now. So after I do the multiplication, of course, which is 0.01787 ... meters to the negative 2 times my fractional uncertainty of 0.008021, and I am going to get, ooh, that's a very tiny number. So I am going to write that with zeros just to be a little visual for us. So that's going to be 4 zeros, 1433. And my units meters to the minus 2. So my final answer is going to include two significant figures. I'm going to need to round this up to 1, 4, and 3 does not round the 4 up, so I am left with 0.00014 meters to the negative 2, and then my actual number is going to have the, let's see, this is my tens, hundreds, thousands, tens, 100,000s place. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Ooh, that means I need to check my sig figs. So that number is 17872. So the 2 doesn't round the 7 up. I'm going to be left with 0.01787. And that the units are going to be meters to the negative 2. Wow, that's a tiny, very tiny number. And this is a perfect time to apply scientific notation. So if you wanted to, you could write this using scientific notation, which then would be 1.787. And then actually, you know what? Might be easier to do it this way, is to do plus minus, and actually have brackets, then use plus minus 0.014. Double check everything is right. And then I'm going to write times 10 to the power of. So notice my scientific notation is in the front, or after all these brackets. And that's going to be 1, 2. So 10 to the power of negative 2. Then I could have put the units in the front here. So then I could have wrote it like this if I want to write it with more condensed form with scientific notation. Okay, wow, you went through all that. Good for you. Guess what? You get to do example 6. Oh yes, and if you don't remember the value for B is, I believe, is 1.3 meters. Plus minus 0.2 meters for the absolute uncertainty. Let's do a quick check here. Yes, it is. Great. Guess what? Good time to pause the video and try it yourself. Then I'm going to play number 6 in fast play.
First thing is we're going to try to find b squared. That was 1.3 squared equals 1.69 meters squared, and which with exponent is 2. So finding the fractional uncertainty of our answers, so take our exponent, multiply the fractional uncertainty of b, and then that's going to give us 0.307 and since it's greater than 2% of our for relative uncertainty, we round it to one significant figure. And then that's going to give us 0.52, which we round to one sig fig, 0.5, and our final answer we round it to the same place value, 1.7 meters squared.
Okay, so that is the answer for example 6. So good luck, good work if you gave it a shot and tried it. Very nice. And you know what? Here, I'm going to type in an inquiry question for you to try, because I'm going to show you something interesting that has to do with why the equation for taking the fractional uncertainty for exponent is the way it is. So here's the question, and I should say inquiry in the front. I want you to try to find the absolute uncertainty for b times b. I know it's b squared, but I would like you to use the multiplication or the division method instead, not the exponent method, okay? So good time to pause the video and give it a try. Okay, so I'm going to do this here quickly, but we know that b times b is equal to 1.69 meters squared, okay? That's 1.3 times 1.3. But now, when we use the multiplication method, this is my final answer for my fractional uncertainty is going to be delta b over b plus delta b over b, okay? And that's going to be 0.2 meters over 1.3 meters, and then I add that up again, okay? Now, you might be thinking, wait a minute. Isn't that exactly the same thing as 2 times delta b over b? And yes, you are completely right about that one with, well, absolute value, whatever. But essentially, that is the same idea. And if you still don't believe me this is going to give you the same thing, let's just try working it out. So I get 0.3076. Hey, that's exactly what we got before, isn't it? Huh? And then, actually, you know what? I don't think hopefully there shouldn't be more need for me to continue this, because take a look at my fractional uncertainty of my answer, 0.307, is exactly the fractional uncertainty we got for question 6 over here. So that if I take this and I multiply by 1.69, that's going to give me exactly the same answer. What I want to show you in this example is the fact how the equations that you use for the exponent method really are built on top of the method we use for multiplication and division. So the concepts kind of form a pathway. Kind of they are coherent with one another. Okay. So hopefully you enjoyed that connection there, or not. That's up to you. But anyways, hopefully you'll find these methods useful for you when you do your calculations. I wish you the best of the luck. This is the last video for Uncertainty Propagation. Kudos, double thumbs up for you for making through all those videos, okay? Thank you for watching. Fan Mama Physics, signing out.